Welcome to Examalist. In today's lecture, we will learn about solid state physics 1. Well, you might have seen various objects around you. For example, a pen, a graphite in a pencil, a glass, a wooden table, an iron stand, a plastic, and many other things like a paper, etc. So these are all made up of different types of atoms and molecules, and they all have their own structure. So in this particular physics, that is solid state physics, we will differentiate between how various atoms they produce various structures and how the properties differ. You know that the property of this solid, they all differ in color. For example, a glass can be transparent but graphite is not transparent. Okay, so it's like depending on the transparency and opaque, wood can be of brown color, and then rusted iron can be of red color. Okay, similarly, color, texture, strength, hardness, ductility, these all the things they differ with the structure. Okay, and based on the structure, we also find that various object has various electrical conductivity, various heat capacity, they have various melting point and many other properties. So what do we need to study? Here we will study about the fundamental building blocks of these objects. Well, the fundamental building blocks of these objects are atoms. These atoms, they constitute molecules, and the arrangement of molecules define the object. For example, a common salt, for example, you might have seen common salt in your kitchen, that is sodium chloride, NaCl. The structure of sodium chloride is like just like a crystal. Okay, it's like a crystal. Similarly, there are various other structure whose various other molecules whose structure can be different. Some can be crystalline, some can be amorphous, like they're arranged in a very haphazard manner. Okay, and then we'll study about the basic building block. By basic building block, I mean the atoms and molecules and their structure, how they arrange themselves, and how various structure lead to various properties. So this is the basic idea that we'll explore. So our main focus will be on crystalline objects, okay, or the crystalline materials. So let's try to understand what crystalline materials are. Now crystalline materials are also called as crystals, and they have a periodic structure. It means the fundamental building block of those structure are periodic. If you repeat the structure, then you can generate the entire crystal. We'll see that. So consider this as an example. Okay, so we have a lattice, we have a basis. Okay, so what do you mean by lattice? A lattice is just an arrangement of points. See, these are points which are arranged in this manner. So these are all lattice points. Now in this lattice, if I put basis, it means in these points I need to put molecules. So if I put molecules, then this will give rise to a crystal structure. Okay, for example, let me give you the structure of NaCl. This is an NaCl structure. You see in this structure that this place contains the sodium and this small place contains the chlorine. Okay, so both the sodium and chlorine, they occupy the space. So these are lattice points. So this is a lattice point, this is a lattice point, okay, and this is also a lattice point, and these lattice points are occupied by molecules. So the sodium has occupied the lattice point. So when the sodium is placed in the lattice point, we say that the basis has been placed at one lattice point. When the chlorine has been placed at this lattice point, we say that a basis has been placed. So what are the bases? So what are the bases of the sodium chloride structure? The basis of the sodium chloride structure are the molecules, that is Na and Cl. So these are the basis of sodium chloride structure. Now what are the lattice points? As I said, lattice point are these points where we can put the basis. Okay, so this is the meaning of lattice and basis. So once you put the basis into the lattice, what you get? You get a crystal. This is the entire sodium chloride crystal. Okay, so this is what is meant when we said that when you put lattice and the basis, you get a crystal structure. Now sometimes these are all 2D crystal structure that I'm showing you. This is a 2D crystal structure. This is also a 2D crystal structure. This is is like a collection of square lattice. So see, this is a square. So if you contain, this is also a square. Okay, these square points are the building blocks. Here the building blocks are this, so a bit different. Okay, so we'll talk about the basic structures. Okay, let's continue. So the primitive cell. So by definition, an ideal crystal can be found by infinite repetition of identical structure units in space. For example, consider this. If I go on repeating this part, I will get an crystal. Let me give you an example. Okay, now this is a particular fundamental structure. Now my plan is, if I go on repeating this structure, I'll get a crystal. So let us see. So I get another structure and I put it here. So what do I do? So I put the another structure here. Okay, and then let me put it here. Okay, so not only side, I can do it in terms of up and down. Let me put it here. Okay, and let me take another one. You see that this fundamental building block or the primitive cell, so these are the fundamental. Okay, these are the structure that I can repeat. So when I'm repeating the structure again and again, what I'm seeing, I'm getting a crystal. Agreed, I'm getting a crystal. So there are various primitive cells. For example, this is one type, this is another type. Okay, this part is another type, so this is another type. If I repeat this, I'll get another form of crystal, but this is not a primitive cell, because if I repeat this, I won't get a crystal, because I will miss this point and this point, and there's something called as a translational invariance. So I won't get a translational invariance. I will discuss that later on. So this is 2D. So this is the primitive cell for 2D. So when I repeated this primitive cell, what did I get? I get a crystal structure. Agreed. Now in 3D, we have this complete part. We have three vectors, A1, A2 and A3. They form a cube, and when this cube is repeated in space, I get a big crystal. Okay, so in 2D, this A1 and A2 are called as lattice vectors. Okay, these lattice vectors are the vectors that define the primitive cell. And in 3D, we have three lattice vectors, A1, A2 and A3. So why they are called lattice vectors? Because if I use these vectors and go from one point to another, I still make the crystal. Let me give an example. So the idea is, take this lattice vector here. So let me take A1 and A2. Okay, so consider any point. So this is a point. Now go A2 up. So if I move A2 up like this, okay, I get another point here, and if I get A1 towards the right, I get a point here. Okay, so these are the basic vectors, I mean the vectors of primitive cells. So this is A2 and this is A1. Agreed. Now again what we need to do is, let us go from this particular point towards right. So how shall we go? We use only the translation A1. So if I use A1, I get a point here, and if I use A2 translation, I get a point here. So you can see that as I go in right by A1 and towards the upward direction by A2, what I'm getting is I'm getting a crystal structure. Okay, so let me continue again. Let me go from this point, let me go up, that is A2, and let me go this side, that's right, that is A1. So these points, they have the atoms or the molecules. Okay, so in this way, from here if I go from any point, if I go, I'll get the entire structure. I get the entire structure like this. So A1 and A2 define the basic translational vector. They define the basic translational vector. So let us try to understand translation in more better form. So consider, initially I am at this point. Okay, so this is the point I am initially at. Now consider you make a translation, I mean you make a movement. So in the x direction, so say this is the x direction, okay, and in this direction if you move, then say this is the y direction. So in the x direction, say you moved by 2A1, okay, and in the y direction, so let me put an I cap, in the y direction you made a movement by A2. Okay, so let me put a j cap here. So what happens now? At which point you reach? You see, 2A1 means you are here, and and just A2 means here, so your final point is here. So you have reached here by translation. So the translation was defined by the A1 in x direction and A2 in y direction. You can make various form of translation. You can make 3A1, okay, plus 5A2. So you can make any type of translation you like. Okay, you define the vectors. Okay, so when you make a translation like this, you see an interesting thing. So when you reach here, if you look at the crystal from here, you look at the crystal from any direction from here, you find the crystal looks same. This is the most fundamental property of crystal lattice. It means if you make a translation from one point to another point, the entire crystal looks same from that point. So if I consider this as origin now, and if I make a translation by A2 and A1, then I reach here. From this point, if I look at the crystal, if I look at the entire crystal, it looks same. So this is translational invariance. So it means if you go from one point to another point in a crystal, the entire crystal structure does not change. It looks same. This is the most basic property of crystal structures. Similarly, in 3D, the translation in 3D, how many lattice vectors you need? See, in 2D you need A1 and A2. In 3D you need 3 vectors. You need A1, you need A2, and you need A3. So these 3 vectors are used in 3D. Let me show you a diagram as I have shown earlier. If you look at this 3D diagram, you see the basic vectors, the basic lattice vectors are A1, A2, and A3. So if I need to define a translation in this particular 3D, then what will be the basic form? Of course, it will be an addition of A1, A2, and A3 vector. Okay. So the translation looks as, any translation T can be written as, say U1 is an integer, so U1 of A1. Okay, so you can have the second part as U2 of A2, and the third part will be U3 of A3, where U1 and U2 and U3 are all integers. Okay, as you can see, I have written down the translational vector that you can see in 3D space. Agreed? So if you make a translation in 3D crystal lattice by this translation vector t, then the structure of the lattice does not change. So this is the meaning of translation. Now this will become very important when we will study about reciprocal lattice. So you must get this point, what I'm trying to make you understand about this translational vector. So let me give you a quick idea. A lattice is defined by three fundamental translational vectors. I mean a 3D lattice. The three translation vectors are A1, A2 and A3, such that the atomic arrangement looks the same in every respect when the view is done from any other vector using this translation. So this is the basic idea of translation. So let us move forward. Now, you see, interesting thing happen in this thing. So consider this particular diagram. Okay. So let me place it somewhere where it looks neat. Okay, so let me drop this part. Okay, and yeah, so look at this diagram. Agreed? Consider a point in blue. So consider this point carefully. Look at this. So I'm drawing, yeah, consider this particular point. You see, now this particular point that I'm making blue, you see this particular point is shared by 8 cubes. So how many cubes are there? So this is cube number 1, back cube number 2, cube number 3, cube number 4. So 4 cube upward, and every upward cube will have a downward cube. So there are 4 downward cubes, 1, 2, 3 and 4. There are 4 downward cubes. So this particular point that I have drawn in blue color, this particular point is shared by, okay, so look at this particular point is shared by total 8 cubes. So what is the contribution of this particular point to each cube? So the contribution is 1/8, since that point is shared by 8 different cubes. So the contribution of this particular atom to each of the cube is 1/8. Okay, so the contribution of this particular point to each of the cube is 1/8, and to the entire 8 cube the total contribution is 1. Agreed? So in a primitive cell, what you see is each point will have, you consider any point on this cell, and it will have total 8 cubes surrounding it. Agreed? So each lattice point is shared by 8 cells or 8 cubes. So total number of lattice points per cell is 1. Okay, because you see, this is, consider this primitive lattice. Okay, now this is a point, so this is another point. So total how many points are there in a primitive lattice? So the total 8 points are there in a primitive lattice. So I'm marking it with the orange color. You see total how many points are there? 8 points are there. Okay, now contribution of each point to this cube is 1/8. Contribution of each point to this cube is 1/8. So the contribution of all the points to the cube is, all the points means how many points are there? Total 8 points are there, and each point is contributing 1/8 to a cell. So to a single cell the number of points is 1. So this is just an imaginary calculation, just a hypothetical calculation that says that each cell contains atoms, each cell contains molecules, and each of the molecules is shared by 8 cubes. So each molecule is contributing just 1/8 to one cell, and that one cell contains total 8 molecules. So what is the total contribution of all those 8 molecules to that particular cell? It is going to be 1. So I hope you understand this point. Okay, so now we'll move forward. So now we'll discuss about two-dimensional lattices. So the lattice is the basic. Every lattice has a basic building cell. Okay. So consider square lattice. What do you mean by square lattice? Okay. So okay. So square lattice will have the vectors in the form of square. For example, there will be a vector in this direction and there will be a vector in the upward direction. Okay, so these two, they form the vectors. So this is one vector, okay, and this is another vector. So these are all lattice vectors. Consider this is a2 and this is a1. So what happens if I repeat a1 and a2? If I repeat a1 and a2, then I'll get a square lattice. So if I go on continuing repeating, so what I'm doing this thing in 2D. Okay, so what do I get if I repeat a1 and a2? So I get a square crystal. So this is a 2D structure. Okay, so this is a square. Now there is another form. We have rectangular lattice. So in the rectangular lattice, what will happen? You will have your vectors not same. So one will be say big one, and say another vector will be smaller one. Okay, so these two vectors, so let me write these names as say a1, okay, and this is a2. So these two vectors, these two basic vectors, okay, they form this rectangular lattice. And if I repeat this rectangular lattice, what happens? I get a rectangular shape in total. Okay, you see the shape is being maintained wherever I go. So this is the meaning of translation. I'm only allowed to go by a1 in this direction and by a2 in this direction. So if I just continue drawing, I'll get rectangular lattice all over. Similarly, we have this third form, the hexagonal lattice. Okay, in the hexagonal lattice, so let me draw the diagram how the basis vectors of hexagonal lattice look. You see here I have drawn an hexagonal lattice. Okay, and let me draw the basic lattice vectors. So one will be in this direction and another one will be in this direction. So if I repeat this lattice vector, say this is a1 and this is a2. So if I continue repeating this vector, I'll get a hexagonal lattice. Okay, that's a fact. So you can do it. That's a fact. So let us continue the fourth one. The fourth one is centered rectangular lattice or rhombic lattice. So how does this one look? So what happens is, take a rectangular lattice. Okay, there will be, so the centered one will look like this. Let me draw them and then I'll show you the lattice vectors. So here I have drawn a centered lattice, and let us see how the basis vectors, how the lattice vectors is gonna be. Okay, so can I say the lattice vectors as this one a1 and this part as a2? No, that would be wrong, because if I repeat a1 and a2, I'll be missing this molecule. I'll be always missing this molecule and I'll get this. So this is a useless way of stating the vector. So we need to find some different way of bringing down the vectors. So another way is the following. So consider two vectors, this part and so you go down like this. Okay, so for example, consider this part and this part. Okay, so if you repeat this, you'll get a centered rectangular lattice. Look at this. So this is rectangular lattice. So how is the entire center rectangular lattice going to look? So there are lattice points here, there will be lattice points here, and there will be an extra lattice point here. So if you draw it, then you will get the centered rectangular lattice. So this part what I'm drawing is the centered rectangular lattice. Agreed? So these are the various forms of lattices in 2D. Now let us look various lattices in 3D. In 3D, there are all total of 14 different lattice. You can see there are 14 different lattice. Okay, so how are they differentiated? Look at the first diagram. In the first diagram, you can see this A, B, and C. The angle is different. Okay, in the second diagram, between A, B, and C, the angle is different. So not only you can change the angle between A, B, C, okay, but so you can not only change the angle between ABC, but you can also change the length of vector ABC. In this manner, you have total 14 different type of lattices that will produce 14 different types of crystals. So this is, if you count this one, there are total 14 different types of lattices. So the triclinic system will have number of lattice as 1. So what do you mean by this 1? Remember what I said, this 1 was the contribution of all the 8 molecules to a single cell. So in the triclinic lattice, you have this, all the contribution of 8 molecules to a single cell is 1. So what happens here, it is somewhat rectangular. See, A1, A2, and A3 are not same, and even the alpha, beta, and gamma, that is the angle between the 3 vectors A1, A2, A3 are not same. So in this manner, you can construct total 14 different types of crystal lattice in 3D. Okay, and they are also mentioned here mathematically. Okay, what happens with A1, A2, and A3? So look at this monoclinic. So in monoclinic, what happens? A1, A2, and A3 are not same, but interestingly, this angle between two vectors A1 and A2 is 90 degree, and the third one has an arbitrary angle which is not 90 degree. So this forms a monoclinic. So let us try to see. Okay, so these are all the 14 different lattices, and if you repeat these lattices, you will get one type of crystal form, and if you repeat this lattice, you will get another type of crystal form. Agreed? So there are 14 different lattices, and we will concentrate on the cubic lattice. In the next part, we will concentrate on the cubic lattice. So let us see. So let me give you an example of cubic lattice. NaCl, that is your common salt, ZnS, these are all crystalline objects. I mean, these are all crystals, and the basic lattice of this cubic is cubic. Okay, it is just cubic. Now, orthorhombic is KNO3. Triclinic, you can have ZNO. Okay. Now we'll concentrate on cubic lattices. So as I mentioned earlier, we'll concentrate on this cubic lattices. So what happens in a cubic lattice? If you give it a close look, you see there are total 8 lattice points. Agreed? So you see there are total 8 lattice points. So one here, and you see the 3 vectors, the lattice vectors A1, A2, A3, they are all same, and they are at an angle 90 degree with each other. So the A1 is same as A2, and it is same as A3, and this is all A. So this is my cubic lattice, but a cubic lattice can be of various types. Okay, it can be of various types. So this is a simple cubic lattice. Okay, why this is called a simple cubic lattice? Because all the bases or the lattice points are at the corners. Okay, we can also have a face centered cubic lattice. Okay, so we can also have a face centered cubic lattice. So consider this part. Okay, so to have a face centered cubic lattice, what we can do is, so you see each of the corner they have a lattice point. Okay, in the face centered, each of the face will have, so consider this face will have a point here. Agreed, this point will have a face here. Similarly, the below, so say the top part will have a point here. So this is a point, this is a lattice point where we can put a molecule. So the backward one will have a point here, so this side will have a point here, this one will have a point here, and this one will have a point here. So there are total 8 lattice point at the corners and 6 lattice point on the faces, and 6 lattice point on the faces. Okay, so based on that, there is a division of crystal, cubic crystal, into 3. Simple. Okay, look at the simple one, the first one. This is a simple cubic lattice where all the lattice point are at the corners. There can be face centered, the third one that I just discussed. Okay, each of the point will contain, so this is a face centered, this is the third one. You see each of the face, so this is one on face 1, so this is another on face 2. So the lower face have this atom and the upper part have this atom, the side part have this atom, and the back part have this atom. Agreed, so this is a face centered. The third one is body centered. So what do you mean by body centered? You have all the atoms at all the corners and you have just one atom at the center. So this is called as the body centered cubic lattice. Agreed. Now don't be distracted by this type of diagrams and don't fall into the thought that these are all vacant spaces. You see lot of vacant spaces. This is not true. They are actually closely packed. This is just a diagram to make you understand, and don't fall into the impression that, oh, there are a lot of vacant space in between. No, it doesn't happen. There are very less volume available. Actually, they are closely packed. Look at the next diagram. So look at NaCl. Okay, so this is the diagram of NaCl. So it is, oh sorry, CaCl. Okay, so it is very closely packed, as you can see. But these crystals, they have a particular structure that might come into simple cube, face centered or body centered. Okay, so they are closely packed. Okay, now we'll come to the next discussion called as Miller indices. But before that, okay, we need to discuss a bit more on these 3 diagrams. Okay, we'll discuss a bit more. So what are the things that we need to discuss again based on the diagram? We will now discuss the terms called as the atomic radius and number of atoms per unit cell and the packaging or the packing fraction. Okay, these are the 3 important things that we will discuss in the next lecture.